season. So yeah, this is Coffee Compiler Club, December like 17th. We're like heading into Christmas here. Anything to do with compilers, language runtimes, garbage collection, typing systems, concurrency. Somebody last week badly wanted to ask questions about inlining and never got around to it. All fair game, reserved right to moderate, never had to do it. You're being recorded live. Recording goes up these days in an hour or two. If we get Theodore back, he's been my go-to man for doing, I want to say note keeping and timing mark keeping, but he dropped and he hasn't made it back. Okay, that's it. I'll do a, let me find, I can't do two things at once here. Let me find there it is. Somebody's doing timekeeping for me. All right, thank you. Anonymous Raccoon. Oh, I love Google's names there. Yeah, so we'll do a quick AA update just because it'll make something happen here. Last week I reported having I got my typing system nailed down finally after a solid year. I think that remains true. I've been busy trying to implement it in the core AA code base, which starts with a giant cleanup of all things I think were failed attempts that weren't going to be helpful, getting cleaned out. So I'm doing a big tech debt elimination, restructuring a bunch of things. So the usual story is a giant higgledy-piggledy pile of goo. I'm back to barely being able to parse small, simple integer expressions, but I got a few of them coming through. So progress is being made. Okay, here's somebody else coming in. Now go find him in the New World Order. There we go. I don't know if I like this path or not. And we still lost Theodore. Fine. All right, somebody else's turn. That was my easy cheesy 15-minute status, 5-minute status.
I've been working on shaving nanoseconds.
Excellent.
And I keep all week I've been cursing your name because I'm trying to make something that's not much more expensive than a plain old virtual call that returns a constant, but
yeah.
It does so I'm trying to get something akin to that, and boy is that hard.
Yeah.
So I'm working on something to compute the memory overhead of any Java object, and so I can reflect early and look at all the fields and do all the padding, and I get a good size. But then sometimes you want to follow the field references inside that, so I have an annotation to follow those, and then if it's an iterable or a map, I may want to follow those. And so it's those conditionals where I'm oh, well, if it's an iterable, I want to follow it. That if, forget the instance of, that's cached, but the if is costing me 5 nanos. And so I'm trying to shave.
You're doing a heap crawl, you care about 5 nanos because you're doing a giant heap
but
crawl?
It's most of the time you're not. So it's the when you're not, the are you iterable? And the answer is no. It's oh crap, but I just lost 5 nanos finding out that I didn't have anything to do. So
iterable is an interface.
Right. So when I reflect on the implementation early on, I see if it's iterable, and part of the data I cache for it is yes, are you iterable? So there's no instance ofs at runtime.
Oh, I see. You're just grabbing a bit and saying
yeah. It's just it's if true.
Yeah, but you're doing this a billion times, or you don't care about 5 nanos.
Yes. Yeah,
right.
I don't care about the 5. It's let's go over a collection of these things. And
yeah. The garbage collection guys have the same issues where they're walking object headers, and there are months of effort and debate wrestling the meaning of 5 or 6 bits, so that they can minimize, for instance, GC sweep times by looking at those bits and deciding they don't have to go do any more work here, or they do have to go grab something else and something, and then it got complicated.
So the route that I'm going now, which is paying some dividends, but it's getting harder and harder to shave anything, is as long as I'm caching and pre-computing everything. So now I pre-compute a function, and I have different ones. If you're not iterable, here's your function. So instead I look up my cache thing and my thing for the class in the cache. And I'm okay, just run this function and it will answer all your questions. And the ones that aren't iterable know to never even bother to check that bit. But it's the extra, I'm paying the extra dispatch instead of the extra if, and it's it pays off,
right.
But it's tiny.
Yeah, dispatch is not cheap either.
I was surprised to see going through, so doing this on, I was originally switching on, so I had an enum for you're not iterable, you're iterable, or you're map iterable.
Right.
for your array
When
iterable.
you say enum, you mean like Java enum.
A Java enum.
Yeah.
And switching, I was switching on the enum, and I switched to instead, I put a method on the enum and then dispatched through that. And that was noticeably faster, which surprised me. Unless
Wait.
switching on enums is actually more expensive than switching on
But
ints.
yeah. Switch on ints. What the hell are you doing
But-
enums?
Is switching on enum actually more expensive than switching on int?
Yes.
Oh,
Because enums have to do a thing where they're like a giant 64-bit constant. And are you one of the following constants?
yeah, but when it's 4 constants,
It doesn't matter. The effort of loading the matching 64 bits and comparing on it exceeds, because it also has to be like a GCable pointerable thing. So it goes to read and write variables and shit like that. You
Why
want
64? Why isn't it 32?
well, it's whatever your VM size is. If you're doing billion size heaps, you probably got a 64-bit heap.
I'm thinking the pointer compression stuff.
So,
okay,
you
so if
know,
you're outside that, right? Yeah.
You go to a small int, and he'll also switch on
but then
to.
it'll be an if ladder then, right? With only 4 possibilities.
I was going to say,
If
how many
it's-
choices do you need before a jump table beats an if?
Yeah,
ladder?
right, exactly. And HotSpot does that math. He also does histogram counts on your trade-offs, and will do jump tables versus if ladders according to what the histogram says, but
It's
not on
always-
enums.
It's always been a little irritating since, I don't know, 1985 or so, how expensive a jump offset is. Because no, seriously, because like it was the same, there was no additional cost for it back on, say, the 8086. I mean, everything was slow, right? But then
Right.
each generation, it's gotten relatively slower.
Yes, it's gotten faster and gotten relatively slower. Yes.
Right, exactly. So it's like, what, why isn't there some instruction?
No,
on,
it's
say,
the same
why
as a
isn't there
jump
some-
register. Your instruction pipeline fetch gets wedged.
but that's the thing. You could theoretically have a more complex instruction that has a bounded jump, right? Because
Yeah.
that's the main reason it blows everything out, is because it's an unbounded unchecked jump. But what if the instruction itself
Yeah.
encoded the set of options?
Yeah.
You know what I'm
Intel tried
saying?
that a few times and couldn't come up with an answer that didn't involve infinite amounts of VAX like silicon or just more overheads elsewhere. There's a translation table lookup and shit like that.
Right.
But they don't, now do an arbitrary function. You can't do that. So you have to have an arbitrary jump to fixed offsets or something weird. But that doesn't help his fetch pipeline because he doesn't know where to start fetching from ahead of time. So your best bet is to go through the branch target buffer, and branch target buffer only is a cache. And if you use it too heavily, you blow it out and then it doesn't cache either. So I'm half theorizing that Mark's hit the branch target buffer cache because he's doing it on enums instead of ints. And you go to ints and you'll hit the regular branch prediction table. And you'll also, because this was done eons ago when switch in Java bytecodes mattered, they get custom incremented counters for the arms in the interpreter and in the C1 and the first year compilation. And now you have a histogram built in by the compiler. And
Okay, cool. And that should beat the virtual.
And that will
dispatch.
almost surely beat the virtual call. Yeah.
Okay.
Virtual
Yeah,
calls
that was that confused me. I was like, how can that possibly be?
No,
faster?
an uncacheable virtual call, a truly megamorphic virtual call is something like 50 clocks, 60 clocks. So it's 3 loads in a row that are all dependent and a jump, a call to a register. So that totally flushes your pipe and repeatedly flushes it because the loads that are all dependent can't be chained together in any way.
Okay. So then a related question there. So you said that cannot be cacheable. So how many versions of that interface do I have to have before it becomes uncacheable? Because again, I'm working with tiny numbers. I only have 4 things that are iterable, right? Iterables, maps, arrays, and none.
Right. So I'm hearing 2 different things here. So if you have copies of code that each copy of the code pings on the branch target buffer, and it's hot, and you're relying on the branch target buffer to pull your predictions out because you're actually wiffle waffling which target you're headed toward, then that branch target buffer probably has a few thousand entries. You blow that out, you lost it, and you're back to 60 clocks a pop. If you don't target the branch target buffer, which means that you are doing an if ladder, which uses the branch prediction table, and the if ladder correctly predicts the large histogram set of choices. You're only 4, it's not very many. If he has that stats in, he won't even touch the branch prediction table because he will mostly branch correctly. And then you'll get your best answer in all cases, and no code blowout issues.
So you're saying the if ladder is likely to be a
If
better
the
choice
if
at the
ladder-
small.
Yeah, if the if ladder collects stats and the stats are correct, like you profile with the same histogram that you're actually running your billion lines through, then the if ladder will be constructed such that you take the 99% case as the fall through, which is a forward branch, which does not touch the branch target, but does not install into the branch target buffer, or sorry, the branch prediction table, because it predicts correctly. This is a sort of a well-known, if you're deep into the, not even x86, everybody's microarchitecture hacks. Backwards branches are predicted taken for loops, forward branches predicted not taken. If you make the prediction direction the same as what actually happens in runtime, like you build the code that you correctly go the right prediction, then he doesn't update the prediction table, which means the prediction table reserves space and bits for branches that are fucked up. So if you mostly get most of them right, and that's the bulk of your code, so every time you write this test and it gets inline and replicated a dozen places, if it comes up to 1,000 of them, you're running out of your branch target buffer's unique code addresses that you can have separate prediction tables for. If they're all predicting correctly, they don't touch the branch target buffer or the branch prediction table, and they all predict correctly because that was the thesis we started from. He profiled correctly, so he wrote the branches correctly. And HotSpot totally pays attention to that.
So does that go back to the switch on ints?
Yeah, the
goes
enum
that
switch,
route?
I don't know what they did on the enum switch, but the obvious thing is they just did an if ladder on testing for 64-bit quantities. I don't imagine they would have put
On the ordinal. So each enum has.
Oh, they
an
have to
ordinal.
fetch the ordinal. I bet
think
you they
so.
fetch the ordinal every time. Yeah, you'd rather have an int. I do this all the time. Like Java enums have a lot of overhead, and I've also, been writing C code forever with the correct macro layout to do stupid.
Yeah. I'm never writing that. Like I forced myself a while ago into stop using ints, switch to enums.
Yeah,
and
go back.
yeah.
I mean, it's like you want the enum that's type safe like the Java one, but the implementation is a fucking byte.
Yeah.
Right. That's what you want, not a garbage collected component where they fucking fetch the ordinal and then branch on that. So I would switch to an int, see what happens, and then tell us next week, because I'm curious to know. Maybe my advice has got stale now.
Well, the thing is, it could be as optimized as you describe. I just don't think they've made that investment at this point.
It's just what?
And at this point being Java 8 from 10 years ago.
Yeah, good point as well. But I mean, there's
I know-
nothing that, like, they could just use a byte. I mean, if they wanted to, and then when you're asked to look at it, they would look up the byte versus the vice versa. So I mean, it's in a strong.
Yeah, right. Yeah, it should be read the worst case, read the ordinal from the thing you're switching on, and after that, it's an int.
And then switch on it.
Branch.
If you do a switch table in the bytecodes, then you have a chance of getting the profiling you want. That's what you'd like to believe. And the indirection costs you something because that load's not going to be necessarily cacheable. Yeah. And certainly not predictable.
In an optimizer in a strongly typed system, you can actually replace the enum object with the int value because it's of that type.
You can't do it in Java because it's not in the bytecodes.
Well,
and my compilation does not include the whole program. It only includes a method which has to interact with all other things. So at the method call boundaries, you went back to being an enum. You could lift it throughout the method, and it might happen that way.
And you could probably lift it across methods if you had a deopt.
Only if inlining right now. Right now, only with inlining because there's no type safety across method boundaries.
I didn't know that. crazy.
I made it too strong a word, but there's no compiler modifiable facts carried across compilation boundaries.
I think there are now with the sealed type support. I think they had to do some of that.
Well, that
Wouldn't
would
they?
be sealed types
Right.
independent of everything else. That would be a new piece of typing system brought in that was VM wide.
What are these boundaries that you're referring to? Is that to a different class or
Sealed classes, they're known.
no,
known to be
but
final.
but forget sealed classes for a
Oh.
moment. You said that there was no
Yeah.
what type.
Yeah.
safe
So
types
you have the
across
Java type system the JVM type system as expressed by both bytecodes and the classic sort of Java types. That's the knowledge that is kept as you cross compilation unit boundaries.
Right. So sorry. Yeah. So what's a compilation unit boundary?
Oh, it's whatever method got compiled plus its inlines.
Okay.
You can go ask that by turning on the right flags.
Okay. All right. So you can inline anything,
Yes.
but then when you didn't, you lose it when you.
Yes, when you
Step
cross the
out.
boundary.
Okay.
That's correct. That's correct.
Gotcha.
That means when you come into a method, you don't have any of those cool facts that you might have had when you left some other method a while ago.
Right. Makes sense. Yeah.
Okay. And when you make a megamorphic virtual call, you always come into it from an immediate prior call. And because you just came in, like it's not inlineable. 4 is not inlineable on all 4 targets. That's a heuristic that I wrote years ago. Somebody may have changed it. Let's assume it didn't. You didn't get inlined at your megamorphic call. Okay. All those facts got lost. You have no facts other than what's available from Java bytecodes. Now this call is tiny. It says do an iterable or not, and then it returns. So you come in with nothing and you return immediately. You get no benefit from anything. You pay the max overhead for the virtual call to get there. You pay, max overhead to load and test a bit, and then you return the bit. All your call is in overheads of getting in and out, nothing to do with the bit.
Right.
So the next piece that I was going to, after you got your enums in there, is expand your enum to include already bits that say I have it, I'm going to be iterable or not directly on the thing, and then your bit test is like check one of my bits in my enum. Somewhere in the world you collect some enum.
Is that different than the enum?
Yes, because it doesn't have any indirection. You reverse it from I have an enum and I ask a question. The enum itself will take a virtual call to virtual targets to pull a Boolean up. Okay, you put a flag in there, which is a field. Now you load a field and test its bit. That's better by the virtual call cost. Okay, now you put an int here instead of an enum, and you reserve one of the bits for saying it's iterable or not. Then you do an and bit test. That's even better. Right?
Okay, right. So yeah, I'm ditching Java enum, but
Yes.
I don't even need, right. So then when I go to the int-based enum, it's the same thing, right? The 4 values I'm going to have are 4 bits that I'm checking, right? Like,
okay, that's it. That's the next better thing. Yes, no indirect loads at all. You're just checking a bit, and then branch prediction will work as best it can be done there without any. And he can prefetch ahead and all that kind of shit. Like you do a load and then you branch on the load. He must ask the branch target buffer which way the branch goes, or the branch prediction table, which way the branch goes. If it's an indirect through the register, he goes to branch target buffer, which gets overloaded.
but now, are you saying now don't even switch on this int? I should just be doing some other comparison?
That's the next step up. Yeah, not yet. I'd switch on the int, but then the next one is don't even switch on the int. And
right.
this
So
is
this would
the
be
same.
the I'm not iterable is value 0. So I should be doing an if 0 or if not 0, then do switch. Like that would be better than
If you have a highly lopsided distribution.
Yeah, let's assume, I mean, the only thing I care about optimizing is the none case. Like if you are iterable, I'm going to be iterating, so who cares?
Yeah. Yes, then you should write an if explicitly because the compiler might get it wrong. He's supposed to profile and do all the right things, and he might not get it right. So you just put your if in and, walk away from it. If 0 over here, else over there.
Otherwise switch.
Yeah. And now go to the next step. I know all these tricks. It's like stupid, but they work. Put the expensive thing in its own function.
Yeah. Oh yeah.
The switch.
Yep. Yeah. Already there.
You want to inline the abstract concept of if null, do nothing, else return contents of other function. And he'll inline that always, and then immediately it becomes in the code. If null, do null, else. Oh, function call. Maybe I don't want to inline it. Maybe I push it over here to inline it somewhere else.
Right. So the if for none of the bits set is not in the function, so it's manually inlined.
Yeah, effectively, yeah. You don't have to manually inline it everywhere. You can put it in a wrapper.
Okay.
But the wrapper wants to be tiny so that it
Gotcha.
inlines. So here, so we'll go down here to the code samples section, and this is this thing here where you say boolean.
So it's a function that contains just the if and then another function, and the inliner can decide, do I want to inline one layer or two?
Yeah. Mask.
Can someone post the Google Doc link? I'm not seeing it in my email.
Should be at the bottom.
I don't have. Well, no, I'm not seeing the email for today's. But thank you, Theodore.
Okay. So other than Google capitalizing, doing weird shit, there you go. Something like that. I mean, I don't know. I wrote. You could even get like excessive, but that's the final should not be necessary here.
Right.
As soon as it's that small, he's going to inline that. And it's still abstract, but yeah.
Interesting. Okay. Yeah, makes sense.
This is the same thinking it goes through every GC engineer's head while they're trying to beat their way through that heap every time. What can I cut out as fast as soon as possible? The very act of looking to ask the question is way expensive when you multiply by billions.
Yeah, exactly. Yeah, getting down to that level, it's crap.
Yep.
I've got a total of like 15 nanos that I want to shave off, and
right.
I started at 100 nanos. It's getting really hard.
Yeah.
But it's like it's the leap week at work. We don't have to be productive, so like why not spend my week
doing
on
something
shaving
fun,
a few nanos? Yeah.
It's stupidly, these kind of questions on that kind of scale can get you integer factor speed up. Still, you can still get another 2x speed up if you drop the next 15 nanos off.
Yeah, exactly. Yeah, it will be real time at some point.
Right.
I'll have to be sure to put it in my status report too. Shaved 5 nano.
Yes, but put the scale factor in there times times a billion times every time I did a heap crawl. Why are you crawling a heap?
It's all about I need to know how much memory we're retaining. So this ties back into, I've talked about this lightweight executor that I built before.
Yeah.
And it has a feature of a lot like the fork join pool of when a thread blocks, I detect that and I spin up a compensating thread to take its place. And then that thread blocks and I spin up another compensating thread. And when do I stop doing that? So I stop doing that when I cross some memory threshold, right? But now I need to know how much memory my running tasks are taking. So I have a way to have my running tasks report their memory usage. And this makes it easy for them because people were doing it by hand and like, always returning wrong values. And so now I get pretty accurate values with pretty low effort.
I did very similar things at H2O, where if you blocked, you had to spawn another thread. And I kept running into infinite spawn cycles.
Yeah.
Which I finally fixed by doing the giant cluster-wide lock ranking scheme. And now I don't infinitely spawn threads and I don't have to ask the question. Separately, I asked the question, how much memory is going on? Because we have big data sets. And so you just have to be aware of how much big data, like I don't.
Yeah, this is some tasks may consume tens of gigabytes. Others may consume, tens of kilobytes.
Exactly. Yeah. And it's all, and for H2O, it was all tied with memory, with data sets. So we would ask the question, you had an API you went through that said, I'm dealing with a data set, and that API tracked the memory consumption.
Yeah.
Indirectly, but it did, because you'd be cluster wide too, right? You're saying tens of gigs. People would load tens of terabytes, right? And it wouldn't fit on one node. It's, your cluster's half gone eating this one data set.
Yep.
And then somebody does something stupid where they want to update some field or whatever. Do I have room across? Can I toss an old piece out? Do I need to go to disk? What do I have to do here? Do I tell the user, no, you can't do this thing because you're out of memory? Or crash for out of memory was the other option. That happened plenty too.
Yeah. So I have that limit when you cross, I stop creating new compensating threads. But obviously the tasks that are running can continue to consume more memory. So I have a hard limit. You cross that and I start throwing out of memory errors at you.
Yes.
Like it's like I'm I will probably regret that decision, especially that choice of exception to throw, but it seems like the right exception to throw. Like really hard to ignore that one, and pretty accurate description of what is happening. You're just not out of real memory, you're out of my memory.
We had a reasonable, I want to say, safe point like thought that when you started a process, we guessed how much you're going to consume based on the amount of whatever and heuristics. But if in the process we started getting GC cycles, we took GC callbacks, which reported some amount of free versus live heap. And then we would start taking efforts to remove things that were cached and could be regotten. And if that started to fail, we could throw an error which halted the computation back to some safe point, which typically a user asked for a job, and kill all temporary data sets that were in the middle. And that mostly stopped us from hitting out of memory death errors. Because the usual story for us is out of memory death was actually death of the cluster. Some node ran out of memory, but he didn't complete a computation. So it's like half wedged. So he didn't participate in the other nodes' proper recovery mechanisms. And so they thought he was just sick and slow when we're waiting on him. And the cluster was, hung and dead. So it was.
I don't know if we've talked about on this call. When I worked on coherence, working on the death detection was one of the things I also spent way too much time on. And we had very fast deterministic death detection. So there was no JVM crashes and you wait minutes. Like if the JVM crashes, we knew in network round trip time.
Oh, the JVM wouldn't crash. JVM would throw out of memory and your protocols would all be fucked. Because you wouldn't complete the protocol that said, I return either I fail or I succeed. You want the protocol to tell me I failed or I succeeded, and here's the answer. Yeah. And it wouldn't do that, wouldn't do either one.
The key with out of memory is you have to kill the JVM when there's out of memory. There is no recovery.
Yeah, right. And we did not have a recoverable cluster at that time. Like we started to and decided that market was overrun. So we went to this state machine cluster. Very convenient, very fast. The JVM went down, and the cluster went down. So it's not what you want to do with the key value stores. We walked away from the key value store market. It was overrun.
So how do you deal with the fact that applications are trying to put in caches and cache as much as will fit in memory, because the more memory you give them, the more efficient they're going to be? Well, simultaneously, you have operators who are like, I want to set the amount of memory on the machine high enough that it never runs out of memory.
You're talking about what they did at H2O, or you're talking about in the general way? Because IBM solved this problem years ago.
I was going to say in the general way, it feels like operators and applications are in this conflict of the operator wants to give it enough memory to fit the working set, and the application wants to expand the working set to fit the memory.
Yeah, H2O, Azul fought with this issue for a long time too. And the answer comes back to the same as IBM did, in the 60s and 70s. That is, you have to have hard resource tracking and hard resource constraints. So you let the user cache as much as he wants up until he hits his own threshold, and then you blow him out and say, dude, you out of memory yourself.
This is don't use weak references as a cache.
Yeah, for instance. Well, or if you're using weak references, it's the JVM and it's JVM box. This is what people do now with Dockers and clusters and shit, like Docker units and VMs and the like. This VM can do whatever hell it wants until me, as a running the real hardware, witness that VM being a pig on my Amazon shared memory machine with other unrelated people, and then I blow them out and let everyone else run. Right, there's resource sharing, but there's a hard limit of what you'll let somebody have if somebody else has paid for and wants it, right?
What we found is Flash is also quite a game changer in this space. Flash storage.
It just pushes the border. It's the same problem. You're out of resources because somebody asks for all of your Flash. Somebody else asks for all of your Flash. You have promised both of them some promise. If you fail to make a reasonable promise, somebody gets a promise broken, they're fucked. So instead, your promise is typically, I'll give you X gigs of flash and X gigs of RAM and X amount of CPU. And also, if there's spare available, I'll let you have it. But if that spare becomes not spare, you have to give it back. And if you can't give it back, I'm going to burn you down. Yeah. I'm going to take it back, right? So the Azul VM and machine had a cooperative mechanism where they would hand out extra memory for better GC cycle behavior, but each individual JVM could be told to give back the extra, and they had 10 milliseconds to give it back. And if they failed, they got shot down by the OS.
Yeah, I mean,
And
the
the
benefit
GC
of-
cycle could run in that time period and hand it back, or it couldn't.
the
You
benefit
typically
of the
could.
flash is the economics of it. Because what happens with memory is there's a pretty steep curve for growing memory. Memory is by far the most expensive component today, by far. 32.
Graphics cards,
What's that?
except for graphics cards.
I'd say it's even more expensive than graphics cards. So server, large amounts of server memory are.
I don't know. I feel like my graphics card problem is I ran out of memory on the graphics card.
Yeah, I have two Titans, so I know about spending on cards, but memory is still more expensive. But the
Did you buy the Titans in the last year
no, I don't think they have a new Titan in the last
or
year.
whatever? It's like graphics card prices in the last
Yeah,
year.
the
quadrupled.
3090,
Yeah,
3090, whatever is the super expensive one.
Yeah, they shot up.
But with the flash, it gives you the ability to actually slightly over subscribe the RAM and still because you have not just a 10x efficiency in terms of cost at the low end, but at the high end that number actually grows dramatically. So when you're talking about larger DIMMs, ECC, et cetera,
This is directly not solving the problem I heard Aaron ask. The problem is resource constraint. You say, I have a new resource which has a better price performance curve. That's great. I want all of it plus 10x more, and so does everyone else. You're out of that resource again. You back to the resource constraint problem, right? So solving the resource constraint problem means that you make a hard promise, and you're allowed to go over budget if you can take it back as part of the promise. That's your SLA on that resource, and you just take it back. Now, it's polite of you to tell the process, hey, you have to give it up in 10 millis, or it's coming back from you in 10 millis, whether you give it up politely or you get shot down. And now the process does what it does in order to live with a mobile constraint border, right? In the case of a weak ref,
And I can send a signal to the
thing,
JVM saying, please give back memory.
and an emergency GC cycle runs, and it flushes all things it can flush, and it just needs to give up X amount of memory, so it doesn't have to cover the whole heap. But typically in an Azul collector, it compacts the worst set of easy pages right away, and then is able to release some amount of OS physical memory pages back. The
Yeah, it's
virtual memory
mainly-
gets holes in it.
That's
no one
convenient.
cares.
I've run into problems because the Python VM doesn't do that. Once it allocates memory,
Yeah, most
it
things
never hands it back.
Yeah,
And
most things
your
cannot
only
hand it
choice
back.
is to kill it.
right.
Yeah,
But
what
the
I'm-
Azul collector can hand it back because it works on this notion of pages at a time, and it can free individual pages. Most collectors cannot hand memory back. So if you let them have optional memory and you want it back, it's death of the process.
what I was trying to get across is that these systems tend to fall over at the margins, and having an answer at the margin can buy you time to actually get a better solution in place. And that's, if you have 100 servers and you run out of memory on one of them, chances are you now have 99 servers and you need the memory of 101. So now one of those 99 is going to die.
Yeah.
Now one of the 98 is going to die.
Yeah,
And by the way,
right.
we've seen this a billion times
Yeah,
because,
right.
we used to have this issue. So
Right.
Now we talk about systems and controls and stability.
Well, what I heard Cameron say is we have this other option, which is slower than memory, but we can push you onto it as a way to say red flag, but you're living in slow land instead of dead land.
right.
Which is helpful if you have a way to send a throttling signal.
And
Be
yeah,
like,
and now,
dude,
right.
please slow down a little bit because
You
you're
have to
about to
go
push me into
upstream
unstable
and throttle it.
territory.
So these are all hard resource constraint problems that, like I said, have been solved a long time ago and get solved in other domains which have resource constraints using all kinds of typical feedback mechanisms. You get pipelines and California aqueducts and shit like that, all have resource constraint problems up and downstream, and you have to have back pressure throttling mechanisms in every one of these things. And comp sci has just been living in this fantasy land that says, we'll just add load until it crashes. Okay. And then
Well,
what
I mean,
happens? Well, it crashes.
just look
Oh,
at
we
how
can live with
many-
the crash.
Just look at how many C programs don't check for failure on malloc. I mean,
Well,
it's
yeah.
ridiculous. Like,
Right.
Well, memory allocation can't fail, right? How could that
Right.
ever fail?
And then we hand in hand with that is, well, there's no reason to check because I can't recover from it anyhow. So my solution is to crash. Okay. And actually, to have a dynamic load, a memory space requires you to have some thinking of something you give up. And then I think it goes right back to what you just said. The real point now is at some point before you run out of memory and die, you have to back pressure upstream.
Right. And you have to have some graceful way of handling the issue where you would otherwise have already died.
Or not let yourself get into the death zone. As you see the death coming, you have to back pressure and say, stop.
Right.
If you send me a request, I'm going to throw it on the floor because I can't handle it. Right. So the easy way to think about this is I take requests and I hand results when the request comes out. When the request comes in, I have to record it. And then I consume small memory, come with an answer and handing it back. But stop right there. You're already toast. I take some memory and I record it. Okay. I DDoS'd you with a billion requests. You only can have chance to gather requests, recording them until you run out of memory and die. Okay, you must back pressure even at that first step.
Right.
A request comes in, I'm going to tell you, stop it. And the next one, I'm just going to throw on the floor.
Yeah.
And I'm not even going to tell you stop it because I can't, because I don't have time.
Ultimately, you end up having to push all the way back to the load balancer. Right?
Yeah. Well, and through the load balancer to the far end, the user at his desktop or whatever, the robot trying to DDoS you, I don't care. They all get the back pressure somehow.
Right. Exactly.
Made that mistake at work recently. We had a system that was fluctuating a lot because some requests took very little time and some took a lot, and put a bunch of Kafka queues in the pipeline so that now it could absorb the threshold.
Yes.
And said that we broke all the back pressure, and occasionally you get this queue that's just like growing to infinity
And then you die. Yeah.
You don't notice it for a while.
Yeah. The interwebs folks, people who actually work on internet throughput in a real way will tell you all the in-between routers with large buffer space break all the back pressure protocols. And they're not actually helpful because you can't tell if there's a better route to send the data through, if it's just piling in somebody's buffer somewhere and they're not telling you, don't send me anymore, I can't send it out. They're just collecting it. Well, they got it, they collected it. But now they're dribbling it out at a byte per second, ding, 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 where you'd much rather route it around some other way. But you don't know that because this guy's got a 10 gig buffer. So your 10 gig download all went into his buffer cache. And then he's like, yep, I got it. I'll send it someday, eventually. This, networking things. H2O went in and out of these sets of problems a bunch. We ended up with big caching that turned out to be you'd rather back pressure than cache. Some amount of buffer cache to cover unavoidable things, but not a lot of buffer because you just rather back pressure.
Well, I found I want to do both. Often I want to buffer something because throwing it out and making them resend it just creates more work for the system. But I also want to scream if that queue gets more than like 3.
No, that's what we did. We back pressure. We took what you sent, and then at some point we just said we don't want to take no more. But you're in the middle of sending something, so we sent you the back pressure signal. But we took the last thing in progress.
So while you're signaling back pressure, you're still accepting work.
Yeah. So I have to have a heuristic that says it looks like I'm going to run out of space here. So let me, start warning you, but stop it. And I had enough slop in the system to take one more, and usually a couple more because you got requests from other people who didn't actually get the message yet. So I wasn't a hard system in the sense of hard real time in the set. There was a pattern where you could have multiple people just barely miss the cutoff message or not get it yet, and all start a simultaneous large transmit of big data to somebody who then tells them, no, but it's too late. He's, sort of promised he's going to eat giant wads of things.
There's an entire, it's called queue theory or queuing theory or something like that. There's an entire field of study around this, and it's amazing how many systems we saw, close to 20 years ago when Java started getting used to save the Y2K issues and replace everything and all that. And what would happen is you'd have these applications, they'd work fine, and suddenly they'd die horrifically. And people couldn't understand what was going on, but it's classic queue theory, right? Because you're on one side of the divide or the other. You're either under 1.0, meaning, you put something in and it comes out, right? Or you're over 1.0, which means you put something in and it comes out, right? And the problem is when you're over 1.0, everyone behind you is even more over 1.0. And the ones behind them, which is you, by the way, because you canceled the first one and put in a second one, you're now way beyond 1.0. And you hit this curve and it just poof, like
Yep.
off the scale immediately. And it's amazing how, like having seen some of the studies on it, how real world actually matches the theoretical disaster studies almost perfectly. It's like, wow.
Yeah, you
I've
better
thrown a-
put backpressure into your system, because if you don't, God will put it in there for you and
Yeah,
design
right.
it less well for your use case.
Somebody will have back pressure issues somewhere along the line. I threw in Little's law link in the chat. It's an interestingly powerful law. It's like stupidly simple and also stupidly like useful. Like so many things apply everywhere. Widely used in queuing theory control across the universe. Yeah, fine.
And the way we explain it is like you want to break your systems, and people are like, what? I said, yeah, you want to break your systems because either you break them or someone else breaks them. And
Yeah.
wouldn't you rather know where they're going to break, right?
Yeah,
So
yeah.
so break your system, find out where it breaks,
Yeah.
because you're always going to have a bottleneck. You fix one, there's one somewhere else, right? You want to know what the behavior is at the breaking point, and that's where you focus your efforts.
Yep. Fun stuff. Somebody was going to ask a question last week about inlining. And I want to say it was Max Bernstein, who's not here. Darn it.
Yeah.
Fine.
All right, so we got an AA update. Yorick, how's your project coming?
York like, wait, what?
No, yeah, I was in the middle of stuff. I had to find my unmute button. I mean, since last week, not a whole lot of progress. Just my compiler working on the type checker. It's one of those things where you start with one thing. You think, okay, I'm going to break it down in small steps, but then you very quickly fall down the stairs and you have to implement 15 different things. So in this case, I was working on, still working on, what was it again? Start off with basically defining type parameters and then their requirements. So the traits that you need to implement before a type can be assigned to that type parameter. And as part of that, the part where I basically fell off the stairs, I needed to implement some code that says, can you actually assign this type to this type parameter? Because when you declare the requirements, you can basically, you specify an interface, but those interfaces can be generic. And so for that, you basically need full support for specifying a type signature. Because you can say, oh, I don't just want to require the equal trait. I want to require the generic equal trait, which takes one type parameter or type argument, which is, I don't know, a closure type or something complex. And so you kind of fall off the stairs because you start with type requirements, and you end up basically having to implement the whole type checker, at least the sort of core logic for it. So that's mostly what I've been implementing so far. It's been going surprisingly well, which means I'm probably overlooking something. But I think it helped that this is basically the third time I'm doing this. So the first time I wrote it in a crappy Ruby implementation. Second time I wrote it in the language itself and sort of carefully thought about how I wanted it. Now I'm doing that, but in Rust. And I think it helped that, contrary to my initial Ruby implementation, where I had too few types in my, well, let's say too few data structures. So I think types is maybe a little confusing with types in the language. But I had, for example, one data structure that basically represented both a class and an instance of a class. And this is sort of from dating back when the language was still prototype based and not using classes.
Yeah, I was going to say that works for JavaScript.
Yeah, because that's the model I had up until I think a year and a half, year or two ago. But so now with the Rust compiler, I'm kind of taking the opposite. I'm having a lot more data structures, and some of them you kind of feel like, yeah, this feels a little redundant, but it's actually kind of nice because you can break up all the logic. Like I made it so that basically references to types and types are two different things in terms of data structure. So my compiler has basically, in this case, an enum called type ref, and there's an enum called type ID, and type ref is used for like owned values, references, and a couple special ones like any type, type errors, that sort of thing. And then type ID is literally just a physical type, like a class or a closure, that sort of thing. But you do end up with this code where you have your function that checks, can I pass this type ref to this other type ref? And you started with a function on the type ref. You then have a function on the type ID. You have a function on, because it's an enum, on whatever variant you wrap. And then that has another function. So it's kind of like you start here, you go there, there, there. Okay, there's a logic. So it's something where I'm not sure if I'm super happy with it long term, but at least so far it's serving its purpose. But yeah, that's mostly what I've been up to. Yeah, and I basically quit my job, so January 1st, this is going to be my full-time thing, at least for a year or so.
I assume that's congratulations and not condolences.
I mean, I voluntarily quit, so yeah.
Excellent. Yeah.
You quit your job to try and build a company around this language, or?
No, I gave that quite some thought. Programming language is one of those things that's pretty much impossible to commercialize directly. Yeah, unless you have some bizarre piece of hardware that you target, and I guess even then you would be providing a compiler. Like some embedded systems, you have to pay for their compiler license because they're the only ones making it.
I mean, the world does contain a few Mathematicas, but not a lot.
Right, I think I don't know if Wolfram Alpha is paid. They probably have a free tier, but there are a couple of outliers. But I think for sort of general purpose language, you're basically 30 years too late, I think.
Right. Yep.
And so the business model then becomes something surrounding, like consulting or I don't know, some sort of hosting service, whatever. But I fear that at that point, if I do something, that becomes the main thing I'm doing, because that's where the money comes from. And I don't want that. Like, I want to work on the language. So at least the plan for the next year is to just work on it, see if I can get it to take off, and basically eat the cost of not having a job. But fortunately, I can afford that, at least for a while. And then long term, probably donations in some shape or form.
Yeah, I mean, the hard part about being in the developer space is developers get paid a lot but have zero budget. So it's shocking. You go hire a good developer, 500,000, right?
I spend more on conferences than I have on tools.
Yeah, so that developer is like, well, I could buy this nice tool for $10 that would make me twice as productive, or use this free one. Which should I do, boss? And boss is like, well, I don't have budget for that. Use the free one. It's like, okay, wait. There's no economic rationality in development whatsoever.
Well, instead, you can spend 6 months and write your own. It'll only cost you
right,
$2,000.
right, exactly.
No, boy, I did startups for a while. That was easy math. What? You want a new monitor? Fuck. Of course. What?
So,
your laptop sucks? Okay. Get a new one. Everyone's more productive with big, good, high quality headphones. No problem. Headphones for everyone. Bosch headphones for everyone in the office. That was all easy math.
In our last startup, we actually designed the business processes around knowing that developers had no budgets, and it worked pretty well. We more than doubled our revenue every year.
Interesting. Okay. Yeah.
So what is your advice if you assume that operators have budgets and developers don't have budgets? How do you build the business model?
You make sure that you help developers at no cost, and that there's something on the other end of that rainbow.
It makes me think of my first day at that startup when I was handed a screwdriver and told to assemble my desk.
Was it IKEA?
$500,000 a year for this? Okay.
No, that's inflation. Back then, it wasn't $500,000. I remember what we hired you at. It was a bargain.
The employment part is interesting. There are some companies that are trying stuff. I forgot what the name is. I never quite understood what their model is, but like companies have some sort of subscription service with them, and then they pay the developers. I think it's like Tidelift or something. I never quite understood what their model actually was. It seemed like basically a middleman, like we take your money and somehow magically the money ends up at the developers, which then to me raises the question why not give it to them directly. But I think an issue there is if you have like a monitor, it's fairly easy to write it off as a business expense, for example. With a programming language, like I think it's probably a lot more difficult, and the average tax authority will be like, the hell is this? What do you mean programming language business expense?
No, software tools for a business. Buying a software tool for a business expense is a totally reasonable thing.
Right. So that was the point I was getting to. Then you need to basically do some sort of commercial license where you say it's still free, open source, but hey, if you want, a quote unquote license and an invoice, contact me. And then you basically, you pay for I don't know, emotional support or something, something silly.
That's what it's for. I mean,
right, and that works. I think,
but support contracts are a thing. So take, for example, let's say hypothetically you wanted to make sure that some key piece of your infrastructure that was an open source project got pen tests regularly, because you don't want log4j to have some vulnerability that you then have to spend $1 million patching by redeploying everything on one weekend. There's not really a good model for the entire Fortune 100 to get together and say, we're all going to put money in a pool together that will pay for you to get a professional pen test once a year.
I'll say, boy, it's not as a Fortune 100 company, but as a small business owner, my experience with software, not licenses, but paying for the software for support contracts, that's what I'm trying to say, was that you got zero support no matter what you did. Your use case is weird, sir. We don't support that. Whatever. I got no support, but I got an official for my investors. Yes, we are, all the software is legit here. Like there was no chance of it being accidentally, illegally obtained, as we thought it was free, but instead we took somebody else's thing because we have a software license that says we paid money for it. Fuck it, it's ours. And so the software license support was for save the investors the grief of a kind of license. A legal battle, not actually any support.
Right. But there's also the NPR model. I want to buy a support contract in the hopes that the company doesn't go out of business. In the same reason I donate to NPR, because I would like them to keep making the show I like.
That happens. I claim that's more rare, but you see big companies saying, yeah, we're going to go fund, but then they turn around and say, well, we'll just hire a developer and tell them to go work on this open source project because we don't project disappear. Furthermore, we actually want some stuff out of it that's important to us that we'll just steer it by weight of engineering manpower.
Yeah, if you want steering, hire someone to work on that project. Don't
That's what I'm saying. I mean, you go from, I just hand you the money, and so the project doesn't go away. You're spending it how you want to spend it, and maybe you're working on the project, maybe not. I want it to not go away. Okay, I'll hand the money to my own employee and tell them, go work on that project, right? And it's much more likely the project then doesn't go away. So there's a small step before you get to I'm just going to hire a guy to go work on it, right?
So those models work, but I think you need to be at a certain size. Like if you're literally just some random person and the project like, hey, I have support license. Like first of all, you probably don't have any users, but even if you do, the average person or company will look at it and be like, yeah, nah, we're not paying for this, because they probably won't exist a year from now. And so if you let's say you're the size of Python, for example, you can definitely do that. You say, our license is open source, but we have commercial license, and then you can do whatever you want with it.
I claim that many of the businesses I worked with were willing to pay for that license to know that they were legit, even if they could clearly use it for free, even if it was obviously kind of a flaky thing, but one of the developers loved it. They pay. As long as the license wasn't outrageously expensive, it wasn't Oracle charging what they do for their database, they would pay because it wasn't expensive and it gave them a little bit more safety for a small amount of dollar.
Right.
So I'm claiming there is a market.
It sounds better to say we bought this license for $1,000 than we donated $1,000 to this project. It's like, wait, why?
Right. If we bought it for $1,000, we got a legal guarantee that it's ours, and we're totally clear. If we paid $1,000 to this thing, maybe it's legit that we're using it, maybe not. I want the contract in my hand. I'll pay you the $1,000 for that contract. It's your fucking toilet paper. Sign it. I'll sign it. We're done. You can carry a donation if you want or not.
So in those cases, with those, because this is quite interesting. Because in my like my thought process is always that companies would generally be willing to pay for certain types of software. So let's say they have some sort of database servers or something crucial to them, and have a license. But then typically where you see those licenses come with extra perks, like you get a email support or priority this, that, whatever.
Yeah, they're trying to they're trying to make it palatable. If that's what their business model is, to make it. If your business model is to sell a license, you make it more palatable to sell it. If your business model is I'm an open source developer having a good time, somebody hands you money because they want a contract, you don't fucking care. You just sign a piece of paper and take the money. It's all happy land, and then they don't expect anything out of it.
And in that case, would it be like a one-time thing or a recurring thing? Because I can see
recurring thing.
Right, yeah. Because I was going to say that this...
if you personally want to make some money but not a real business out of it yet, go to a license that you say is an annual renewable and a modest fee, and people will just pay to make sure it doesn't disappear or that they're legally covered.
Yeah.
If you want to make a real business out of it, you need to have the game where you have serious project that has the open source starter version and the closed source, business, whatever, extra things. You get into security and LDAP support and steady updates, and there's a bunch of other things you could do to sweeten the pie. You look at other people's offerings for what they have for the free version versus the industrial paid version.
There's the bad news though, which is in general, no company is going to spend for something that they don't have to spend for.
Yeah,
that's so it's like no one pays Oracle because they want to.
Yeah, there's a cap on what you can get in this model. Yeah,
I love giving money to Larry Ellison. It's my favorite thing.
He loves it when you give it too.
It's always fun seeing him get a new boat.
Yeah, exactly.
I'm just gonna bite my tongue on this one.
There's a reason I named my I'm teaching this semester, and I named one of my projects Sear PeopleSoft. My co-teacher was like, "Don't fucking do that. You're gonna get sued." And so we'll see. And it's all public on the internet. It's a matter of time at this point.
Oh, come on.
Max,
how many lawyers did they employ?
Did you have a question about inlining?
It's not really a question because the hard part of inlining is like the merging of the CFGs and the optimization shit is done. But it's like, so for context, I'm working on a Python JIT. I'm inlining functions into other functions. It's great.
There's your mistake. You're working on a Python JIT. Fine.
I don't know. It pays. Right? The compilers and
no. Go.
And if you hear a big fan, it's because my computer just decided to install Xcode on its own. So I'm inlining functions, it's great. But the hard part is supporting all of the weird shit that Python supports. So like randomly poking at the frame, you have to reify the whole thing, etc. And so I'm just working through several crashes related to the way Python raises and catches exceptions.
Yes, I knew you were going to head there. Been there, done that. Man, what a pain.
It's garbage.
So in the land of C2, I shoved everything, including the exceptions, into the IR. No exception, you went into the IR. And I could do everything with exceptions at that point, but they first had to get in the IR.
So we deopt into the interpreter. So this is the deopt.
Yeah. And then there was a deopt path that took you back to the interpreter. Yep.
Yeah, so that's what's causing me trouble.
Yeah, okay.
Right.
That's another
but there's
method.
like actual Python code in the world that people care about that ends its loops by throwing the stop iteration exception.
That's handled separately. Yeah.
Oh, okay.
I understand that
okay.
design decision still exists, but it's fine.
Right. And if you throw the exception in the IR, but you did it different ways, it's all good. So I caught those in the IR. And said,
I'm pretty sure.
Made a computer to go to out of it or whatever. It's all good. Yeah,
that's how the table, they've got the little exception table thing in Java, right? Yes,
that's in the Java bytecodes for the semantic meaning. No one ever does, the interpreter does that, but the JIT eats that table and turns it into and makes it inlining and catches and nests and wires it all up in the IR, and then the
until
IR
very recently,
the fuck out of it.
And we're not on this version of Python yet, but until very recently, Python had the block stack, which is exactly what it sounds like, where you push and pop exception handling frames.
Yeah. And then the deop path I can talk you through what Java does. It's going to be different for you, but not. There's some things that'll be the same, but it's an
Sure,
ugly thing.
yeah.
So there's the JIT ends every compilation border with a here is the complete save points. Here's a complete mapping to the Java virtual machine architected state. So the JIT keeps around information that the interpreter needs, but the JIT does not need, in case you flip out to the interpreter here. Then there's the magic remap step, which
Wait, shit, I'll be back. Tea kettle's done.
never mind.
Oh, well, he's gone. I found 6 nanoseconds. Everyone.
Excellent. Where from?
Not from the switch. I just found it if I could get rid of.
Well, that's 2/3. It's 1/3 of your problem solved.
Yeah.
I was gonna say one if bought you 6 nanoseconds. I usually think of an if as like 2 nanoseconds.
I run my computer underclocked while performance testing, so it doesn't turbo boost off and screw up the numbers half the time. So I'm running at like 1 gigahertz or something.
Yeah, it would be. It oughta, coulda, shoulda, woulda be 1/2 to 1 clock if it's predicted right. If instead what you did is you removed a load that you had to test a bit on, and that load cost you an L1 cache hit of 4 or an L2 cache hit of 12 or 20 clocks, then that's your gain.
This should have been in cache. This was like
Okay.
constantly reading something that didn't need
And
to
is
be
that
there.
branch predictable? The branch was highly
It was-
predictable.
It was completely predictable.
Okay, and that's
It
how
was
you
a,
got rid of
static Boolean that I set to true at startup. It never
Then-
changed.
yeah, then I'm curious where you got 6 from, because you'd have to lay out to do the math, and we're talking about shaving 6 nanos off of a 15 nanosecond issue.
So how much time is considered a good amount of time to spend in the JITted code versus the interpreted code?
Oh,
It feels like both JVM and the stuff that Max is working on deopt a lot and under a lot of circumstances.
That's kind of a
but-
weird question, right? Because the time should shrink as your JIT gets better.
it 99% of the time, you know, something like that. Every ounce spent in the interpreter, and you must have some, is like wasted time by a factor of 10-fold. Roughly speaking, on average, interpreter is 10x slower than a good JITted code.
10x, wow.
Right, but if I can get 90% of the code into the JIT, I'm still spending half of my time with the interpreter.
Yeah. So that's what I'm saying. You want to be 99 or better. You want to be way up there. If you're only spending 90%, what it really meant was that you barely had a loop that ran, 20,000 iterations, 10,000 in the interpreter and 10,000 in the JIT plus the JITting time or something stupid like that. He just cut you in half. You expect that you're going to
My concern is that Python is so exception heavy that you might just be spending a lot of your time in the interpreter.
that's the wrong mindset. It's whether or not you're going to be in the JIT or not, because if it's exception heavy, but you JIT and the JIT reads all the exceptions and just wires them up like directed go-tos, then there's no exception and there's no cost in the exception. And the HotSpot JIT does that if he manages to inline the throw in the catch site. He'll wire them up. So you don't necessarily pay anything for the exceptions in the JITted code.
That's because most exceptions are pretty local.
That would be, yeah.
We're unlikely to jump super far away.
Yeah, the nature of the Python code in question that you can manage to throw and catch the exception in the same piece of code and just don't have an exception per se, you just have a go-to.
In this case, it's the caller is, I don't think it's actually related to exceptions. I think I happen to catch it in something that throws an exception. I think it's related to an optimization or a load and call method, but like, and some temporary is getting freed somewhere somehow.
Yeah, you have a bug he's tracking, and Aaron's asking a performance question about a bajillion exceptions, right? And the answer is performance is free if, and then there's a big ass if there. So you have to look at that piece. What was I telling you about deopt? What the fuck did we do there? So we jumped into the VM. So at the end of the JITted method where you decide you're going to bail, you jump into the VM, which was like C code, and you deciphered the situation and you grabbed all the metadata and you put it carefully in a set of structs off to the side where it was packed neatly. Then you jumped into a piece of handwritten assembly code, and the handwritten assembly code popped the call into the C routine, popped the call for the function that got deopt, the jitted function. So your frame was completely unwound. Then it had this data structure sitting off the side that it just essentially mem copied onto the stack. Except that usually assembly code was responsible for putting in call return points in the code. So it was just putting, in HotSpot, we could lay out the side thing for the assembler, handwritten assembly piece to load in generically across all architectures up to how to do the return instructions, which varied from architecture to architecture, and also how to do windowing, which varied from architecture to architecture. So there's a couple of these things you couldn't do. So the assembly routine would then read this very canonicalized thing and populate memory accordingly, and round off and add and shift and pad as appropriate, throw in the returns. And when it got to the bottom, it had packed in a bunch of interpreted frames, and then it jumped off to the interpreter saying, and here now you're ready to go. So
we make the interpreted frames after. So we've got this like view of the stack and of the registers that were set, and the whatever, and then we go and then like for inline functions, deep or whatever, go make a chain of frames and then reify them one by one, and then resume.
You build them on the stack and then you fill them in.
Yeah. Two separate passes: build, fill, and then resume bottom up.
And we went back and forth. I want to say that we did something like that at least once. We had generic stack crawlers that were willing to do, but the C code that was going to fill your stack couldn't be running on your stack.
Yes. So this is because of the Python heap frames.
Oh, we have real frames. Oh, I see. Yeah, no, that would work. There's definitely code in HotSpots to crawl frames generically as like a linked list of frame-like things. And the GC does this because it's a different thread crawling this guy's stack over here. And so he can crawl like that. The other one is that you self-crawl when you've pushed the GC entry point, whatever, down below all your prior frames. And then you want to crawl them to collect all your roots yourself, and then unwind and carry on. But for deopt, a thread can deopt itself, but it jumps to a piece of machine code or handwritten assembly code, and it has a very simplified or whatever canonicalized structure off the side to tell how to remap, and it just remaps the stack.
We've got something pretty similar. The heap frames are C Python. We can't change that.
Okay, so you already have. Yeah.
But we don't do a new C frame every function call. Most of the time, it's this lightweight 2-word. Like we call it a shadow frame, and it's got like the previous and some data pointer that's metadata for reconstructing stuff. Which is good for the sampling profiler too, because it goes and it's like, what's the stack? And then people can see, oh, this takes a lot of time.
You can't change the C frames because you're trying to maintain CFFI, or?
We are a JIT on top of C Python. There's sort of two. We'd like to keep the delta as small as possible because rebase.
Your interpreter is C Python.
Yeah, it's C Python, and there's a JIT folder. And we do upgrades every so often. So that's one thing. The other thing is there's this like morass of C extensions of a size I don't know, and even if I did know, I couldn't tell you, that we have to keep compatibility with, and they probably do unholy things. So it's like all the Python C extension code in the world somehow is used for our application.
What's the name of your project? Is this PyPy?
Cinder.
Oh, Cinder. Okay, I don't know Cinder. Fine.
So this particular part of the problem sounds very similar to what Rubinius had in Ruby. It was a Ruby implementation written partially in C++, partially in Ruby, but it had a JIT. But it also was the only implementation at the time that at least claimed to support all these C extensions. I was one of the poor bastards who helped out on that part. Yeah, if you're getting into the be ready for a whole world of hurt. I don't know if the C API in Python is specified anyway. The Ruby API, at least at the time, was not. So you get two extensions. One uses a couple of common functions, and the other one uses functions that are basically supposed to be private, but because C doesn't have any visibility, they're public. And so these people are like, I'll use that. And often those functions, they wreak havoc if you have a JIT or a different implementation or something like that.
That's the same state. There is a notion of like C Python has a CPU processor variable called like limited API where you have that divide. But this is more like, Maxime, I will not attempt to pronounce her French last name, but she works at Shopify. She's got YJIT, which is a JIT inside of whatever the canonical Ruby implementation is called. But if you search Facebook experimental / Cinder on GitHub, maybe it's Facebook incubator, I don't remember. I think it's Facebook.
What's the
incubator.
spelling of Cinder? Just the standard.
Like the fire. CINDER.
The Lunar Chronicles, a book. Probably not. How about libcinder.org?
No, good.
No, twice.
Try Facebook, github.com / Facebook incubator / Cinder, I think.
Yeah, let me throw in Facebook here. Facebook. Okay, there you go. Boy, I got Y Combinator. I don't have a.
Thank you, Aaron.
Yeah, it was GitHub. I was looking for if there was a report. I didn't get
No,
to
we are.
There you go.
I am trying my hardest to get us to write something. It's been a process involving several team switches due to circumstances.
Yeah,
But
yeah.
either we
I
write
would
something
listen to
here or
that
I go
conference
grab
talk.
Logo.
I would listen to the conference talk of here's how we built a JIT for Python.
What's his face? Do you know if Phelan gave one at PyCon? Maybe 2 at PyCon. Matt Page gave one at PyCon a couple years ago. So there are some talks. But I want to write like the paper. It's like we did these things, and it's like we used this. One of my former colleagues wrote the SSA paper we use, which is cool.
Right, but it feels like the C extensions both is the nightmare and is the key. Like PyPy didn't take over the world largely because it broke some C extensions that people needed.
That was my previous project. So my current project, it's pretty easy to keep compatibility because we keep a lot of like the same ABI, almost whatever. My previous project was ground up interpreter for Python. That's called Skybison. It's Facebook experimental / Skybison. And that was like new object model, new implementation of C API functions, everything from scratch. And
Skybison?
Skybison.
Is this the cartoon with the
That's a great show.
airbender dude?
I can neither confirm nor deny any relationship to any cartoon. I did pick the name.
I love that show. And then the Fire Nation attack. My kids
I
had
don't
the
know
meme
anything
of-
about this.
Yeah, then the Fire Nation attack was our meme for 5 years or more.
Cinder was
What
the
do you
fire.
have against Oracle? Come on.
Larry Ellison as the Fire Nation evil overlord dude. Yep.
I mean, to be fair, Fire Nation got ahead of it with technology nobody had at the time. So
Oh yeah. Well, they
I
had,
mean, there's the well-known acronym of Oracle. I'm not sure if I can say it out here, but it's a one rich asshole something.
I mean, Oracle, Ozai.
yeah, right. Yeah, exactly. All right, fine. Fine. How do
so
you do?
aside from the politics, how did Skybison compare in speed to Cinder?
So pretty competitive. So it was just an interpreter, right? There was no JIT until like the very last moments when I did a sprint in a cabin in the woods to write a JIT, which was a nightmare.
Sounds like JavaScript.
Yeah, except with less nonsense. Better politics. So how does it compare? The interpreter, it was on par with the JIT for Cinder. So like the object model was, and then the inline caching and stuff was pretty compelling. And I think with an optimizing JIT, it could have been phenomenal, but the risk was just like how many C extensions. We had to recompile all the C extensions because we didn't have any, you couldn't reach into, you've got like a PyObject struct and it's got like OB item, OB ref count, whatever, all these things, OB type. And we just didn't have that because they were opaque handles, basically. And so you have to recompile all the C extensions. And then some of them would expect certain ref counting behavior, like you could dump something in a a module somewhere and its handle would stay alive, and that's not true for us because we had a GC and like we maintain the invariant that if you had a handle, the heap object would stay alive, but not the other way around because we wanted to get rid of the handles as quickly as possible. So we had like a mixed mode kind of playing fast and loose JNI type thing, and it was a little bit crashy until you used the newer APIs, which not everybody was using yet. So it was like, do we upgrade the world? Maybe, you know.
You make an internal, you know, whatever, Facebook only.
I was going to say, forget update the world. I'm not sure you could update the Facebook repo.
Yeah.
Yeah, it was. So anyway, I don't want to talk too much about like why decisions, but the project's open source. That took a couple months to push out, but you know, maybe if anyone works in a Python shop and would like me to consult, you know, I wouldn't say no. I'll get you on Skybison, sure. It was a lot of fun.
Yeah.
And I don't know about Skybison, but I know we've tried PyPy a few times and always ended up back on CPython.
So PyPy is interesting because it doesn't have the same predictable performance, right? You've got the tracing JIT, you've got some performance cliffs, and they're fixing that. They're doing a great job. We've been talking with the PyPy folks a lot, but it's not as predictable as like our interpreter, for example. Worth a shot if you've got a lot of Python code and no C extensions, especially.
And your concern is that at web app scale, jitter ends up being a real problem.
Jitter? Oh, yes, yes. Sorry, I misinterpreted that as just in time.
Jitter as in inconsistent latencies.
Yeah, inconsistent latencies, or like it just doesn't compile the stuff you want it to because it's not like straight line math code. It's like 50 billion method calls. You know, there was some PyCon talk 3-4 years ago where we were like, by the way, everything is load adder and load method and call method. That's the entire application. And you know, you can inline some of that, but unless you inline the whole thing and like whatever, it's not really consistent. But
This sounds very similar to yeah, Ruby. Surprising. Not really. Like the main alternative nowadays is JRuby. There have been many over the years in various shapes and forms, but they usually die off because they don't support C extensions, or they're not really like they just don't support a lot of Ruby in the first place. But JRuby and Rubinius were the closest to. Rubinius failed for a whole bunch of reasons, big part political. Not going to go in there, you need alcohol for that, but there were issues like years ago. I looked into Rubinius at a previous employer because we were doing a lot of concurrent IO stuff and figured, hey, this would be beneficial. Because I think back then, CRuby, the main implementation, some IO it could do in parallel, but not all of it, and not as much as nowadays. But also we had this mix of IO and CPU driven, and when you do CPU stuff, Ruby just doesn't do anything in parallel, basically. And so we looked at Rubinius and JRuby. And Rubinius at the time was more interesting because we had a bunch of C extensions that we knew JRuby did not support, and there were no JRuby equivalents for it. But it's very similar, like, you know, the base, sort of, if you set aside the JIT and everything, it's going to be much slower, and then you have the JIT. Sometimes it's going to be faster, but plenty of times it's not going to be, and you end up in this case where, oh, you know, the garbage collector doesn't like it when we put this load on it. So it's, I think nowadays at the stage, JRuby is, if you're not depending on C extensions, it's, I believe, fairly easy to switch, especially if there's a JRuby equivalent. But it's something where if I were to start a big Ruby project today, knowing that, you know, maybe 5 years from now I would need parallelism, I would probably start with JRuby from the beginning. Because if you switch over a big project later on, it's a pain. Like when I joined GitLab about 6 years ago, this is actually what I looked into. Part of it, can we switch to, for example, JRuby or Rubinius? And the answer very quickly was just no. Like, it's going to take years basically to change things around while still continuing to develop. So you're sort of constantly playing catch up.
It's a big challenge with the attitude of like, well, if you want it to be faster, write a C extension. now you have this world of C extensions, and you're like,
Honestly, I
Yeah,
think that's one of the things Java really shines for. We were surprised when we started trying to test ARM servers, and you try to move node stuff over and you're like, oh, there's all these C extensions we didn't realize were there and need to be recompiled. And you try and move Python stuff over and it's full of C extensions, and you try and move. But the Java code, you switch it to ARM and it just works because Java projects are actually written in Java. Whereas Python projects are written in C, and Node projects are written in Rust and C++. And
there's some core control logic in Python, and then all the interesting performance bits are all in C. It's it's a nice API for calling C routines. I've heard that before.
Yeah,
I'm
I
not
would
a
go
big
as far as
Python
to
guy.
say there that I think if you were to start a language today, offering a well, if your goal is to at some point have multiple implementations, offering a C API is a death sentence. Because those, you're immediately basically restricting all those other implementations to also be written in C, more or less. And to
people
be
eventually like to put pixels on the screen.
yeah, and
I don't want to write
crucially,
assembly code to talk to
Java has the native calls, but the wrapper layer is really opaque, really
Right.
opaque. That's
but it's also like you
Java
leak.
doesn't really have native calls. Come on.
It's
No,
like
I mean,
you
it's
leak abstractions. Like this was a thing with Rubinius. We had this issue where supporting C extension functions itself was not the biggest challenge. Like we had the sort of framework in place for it. But the problem is a lot of these functions, they expose C Ruby internals that they just didn't apply because we did things differently. And so you have to start essentially emulating those inconsistencies or go to like 50 different extensions, be like, hey, you know, please fix this. And most of the others will be like, no, because it works on C Ruby. You know, I don't care.
Right. You can't do that.
I talked to someone at work who had an interesting flip on this, which was which I had never considered for one reason or another, which was, okay, you're writing a new runtime. Don't do the C extension. Instead, provide a really, really simple FFI shim.
Yeah.
And then all of the C extensions, you don't reach in, you don't say, oh, Python, give me an object. You provide your own data structures, and then from within the VM, you reach in and create the objects. Problem solved. No weird GC things, no like whatever.
You have to copy in, copy out. You have a hard firewall around. I claim that's what Java did, and it worked.
Largely what WASM did is you can hand a byte array to a thing, and you can get a byte array from a thing. And if you want that to mean something, pick a schema, go for it. Like, here's what you've got. You've got send message and receive message, and it's a byte array. Have fun.
And be done.
yeah, and by the way, the entire data model for WASM is a byte array.
Yeah.
Woohoo.
Has anyone considered doing gRPC, but for every function call?
I'm sorry, doing what?
You know, like having an RPC. RPC message passing. You know, do like a protobuf for gRPC, like for everything. That would be a fun shitpost project.
Like
I think you want to look into ambient talk. They sort of do that. It's not for everything.
Ambient talk.
Look at Elm. The language Elm does something similar with ports.
Well, 20 years ago, Microsoft did the same thing, except instead of gRPC, they used SOAP and XML. And it was a predictable disaster.
Within the runtime?
Which one?
They were trying to pressure everyone to do it, but no, not within the runtime itself.
Well, okay. This is why
Microsoft's Midori operating system did a lot of that. That their interface description language was also a struct description language for function calls. So the RPCs in Midori were very similar to the function calls in
Midori is great because it produced a whole bunch of great blogs.
Yeah, so ambient talk is basically small talk, but with the actor model. And they have this whole system where you can register actors across the network, and it uses some sort of RPC mechanism to send messages, but they look like method calls, I believe.
So is it like Erlang, or is it like?
No, it's basically it's basically small talk, but with an RPC system, if I remember correctly from reading, it's closer to an RPC than Erlang's approach of you can just send any arbitrary data structure, and the quote unquote message is that data structure. Whereas an ambient talk, it looks more like message as in an identifier and a set of arguments, essentially.
It's funny. I'm gonna export it to GitHub. It's on Google Code. Oh,
They should have a
Yeah,
working
go to
website because it's still sort of developed.
Go to the links and
I think it's pronounced MID or spelled MIDORI.
Let me see. I have the website. Yeah, there
Yeah,
you
it's
go.
Joe, what's his name with the good series on error handling blog.
Oh, Stefan Mar has a fork of ambient talk on GitHub.
Yeah, joeduffyblog.com.
move it. Somebody move from the chat to the doc, just so we have a record here. Wow, what is this one?
Yeah, he's a really good writer. You know, I love reading what he writes, even if I disagree with a lot of it, because, you know, it's very well, you know, it's problems we've all seen. I don't like his solutions, but I like the way he describes the problems.
Yeah, their solution did seem to be async everything all the time.
Yeah,
which kind of hurts my head.
Yeah. Well, H2O internally went to async everything.
I mean, I get that async everything is good for like physics, but I don't have to keep physics in my head.
Yeah, it was boilerplate was obnoxious, and
does anyone remember Linda tuple spaces? That was a 1986 language, and that was a little bit like RPC for everything.
Yeah,
right. I remember that coming around.
Right, but it was a passive RPC.
Yeah, right. We just threw things into the bucket. And then everyone pulled out of the bucket.
Yeah, that was Galenter, right? David Galenter, one of the Unabomber victims. Yeah.
Oh, I don't remember none of that.
And what's his name from Sun, who lives here in Boston? The guy who came up, Jim Waldo. Yeah, yeah.
And Ken Arnold did a lot of Genie spaces too, Java spaces.
Oh yeah, that's right.
But Galanter, you know, he wrote a book called Machine Beauty, which might have, I wondered if that's what got him noticed by the Unabomber, Machine Beauty.
Yeah, I forgot, Bill, you're like the expert on this topic here. Yeah.
Well, that was a long time ago and I forget a lot, but yeah, we talked a lot about Linda, but I never used it. It was kind of Java spaces was.
So Jim did Project Darkstar at Sun, which was the giant Linda-based gaming backend, if I remember correctly. Darkstar, does that ring a bell?
Maybe it was Secret, I don't know.
Darkstar runs a bell, but not, and Linda, but not gaming backend. I don't know.
I'm confused by the description I'm running. This is an array processing Smalltalk?
Not an array processing. Linda or
no
Java spaces? This is associative memory.
So Linda, tuple spaces, Java spaces, those are kind of all synonyms. So Jim was involved with the Ginny design and the Java spaces design.
Up a level, what is the thesis of this language or architecture?
So it's basically a space you can publish into and query off of. So it's like a queue-driven system, except nothing's actually a queue. It's more a space. I don't know, Bill, is there a better explanation?
Like a relational table? Or?
No, it's read, take, and put, or I don't know if that's what they were called. Right into it, you can read from it and you can take from it. And it's a tuple. So it's just a horizontal thing with things in it, and you can leave some blank. Null is how they did it in Java spaces. Means I don't care. That's like a wild card. And then it matches. That's it. Put it in.
And it was called tuple spaces for a reason, right? Like it was literally a space full of tuples.
Yep.
You can, the wiki is fairly short and fairly readable.
Yeah, and JavaScript just added a type, a nominal type to the tuple, essentially. So that had to map also.
Where they went through.
That was another added element to the tuple, remember.
They're trying to break the thinking patterns of how you looked at computation. And, you know, they're coming around to, you have things you want done, that means other things you want done. You put your intermediates in the space, somebody grabs a piece of work out and goes and puts something else back in, and everything's asynchronous everywhere all the time, but everyone can work on basically a vast giant pile of shit, which is some of it queued as queues and some of it just like a shared memory scratch board.
You could implement a queue on top of it, I think. You would have to do that yourself. But the other thing is things would pop out, like the whole idea was distributed systems are unreliable. So if a node dies when it's trying to process the job or something, then that would, the lease would die. They had leases. The lease would expire and it would pop back into the space, somebody else could take it, that kind of thing.
Okay.
You could use it for that if you wanted to, distributing.
Right. I know they were trying hard to get it distributed. I remember that part, but I was just like, oh, I never.
I don't. No, actually, I didn't remember that well, somebody did. There was a company.
No, I remember that the distributed effort.
Did it. But what this was that initially when they came out with that use case, that the space itself was a single point of failure. It wasn't distributed, right. And some company made one that was replicated.
I thought the design architecture overall required you to be a single point of failure on the space.
Yeah.
So there was giga spaces, they're still around, they did a distributed one. And then there was some company in the UK that did as well.
Okay. Yeah, that's right. That might have been Nigel Warren.
Nolan Richardson or something? Richardson. Yes.
Yeah.
It sounds like you could implement the entire thing on top of a distributed hash table if you wanted to, and let nodes sort of come and go and just handle whatever work happens to be in the work list right now.
If you want to have some reliability, you still have to have some way to replicate data for failure nodes. If people are going to come and go, when they go, they took with them what they took with them. So you have to have replication.
Yeah, there's a lot of overlap because Gigaspaces was one of our competitors, Tangasol.
Right. And they came and bait on our door a bunch of times because they had performance things they were trying to do and asynchronous bugs they were trying to work out, and they were wondering what the JIT was doing. And the Java memory. I talked to Gigaspaces folks a bunch. A long time ago. I said a bunch, but 5 or 6 times, but over the span of a year or 2 years. But in the
Oh, yeah, I remember. I actually remember a conversation with Cameron about Gigaspaces doing something for free, and you walked away. I think he said no. Yeah, I remember that. Oh, I'm really old, and so all these memories are sort of buried and lost.
It may be better that way,
Yeah,
like tears in the rain.
Yeah,
lost in time.
I have some memory cycles that remember that hex C0 and the sequence of nibbles that come after that are the Z80 call instructions.
Yeah,
and those are brain cells that should better have been used other ways.
Somewhere I've got my old code, my old assembly language. It'd be fun to find that in the garage. I have a database in the garage. I shouldn't really show this to the world, but that's my database. It's not very organized. It's in there.
Yeah, right.
But anyway, I did have one question that I was going to let the inliner go, but you one time, like a couple sessions ago, you said racy for all, which I assume is you're letting multiple threads hit something unsynchronized.
Yes.
What use case?
I have a lot of them.
Racy for all, and I wouldn't recommend it.
Oh, no, I have a lot of use cases.
On the internet.
Well, okay, the obvious one is you have a large shared concurrent hash table. You're caching for a web server. You have a web server that's taking requests from all over. He's launched a bazillion threads to handle bazillion parallel requests. Every one of them go to a common shared cache.
Yep.
The cache, from his point of view, he's getting racy reads and racy writes from all over the place.
Right.
And that's a common use case. And you need large shared cache for multi-threading.
Yeah, but wouldn't you make that a concurrent?
Yeah.
I mean, someone actually.
Yeah, as soon as you say concurrent, it's racy.
Oh, okay. So racy for all didn't mean unsynchronized. It just meant non-blocking, probably.
Yeah, it's unsynchronized and non-blocking.
Oh, it is unsynchronized, but it's concurrent. It's like CASs.
Yes.
Make sure that
Yes.
it's.
And all locks start with a cas.
Okay.
So you can't escape the cas. You must have the cas whether you lock or you don't. Now,
So-
if you go to a cas without locking, then you can have this much lower latency, higher throughput, yada, yada. But you have to deal with the, you know, the asynchronous nature. And when I say racy for all, there's other places where racy for all comes up. So I don't know what context you can. I do it a lot with performance counters, where it's okay to drop some bits.
Right.
I do a lot with, I think about performance counters where you have to use cas instead of not versus cas, because under heavy load, dropping bits means that you drop them in a very specific way that blows the usefulness of a performance counter. What's another good racy for all? There's a lot of them where I have a one shot first person in, flips the bit, and then it never flips again. That's
Resizing something, two people are
initializing.
allocating and they're racing to see who can update the pointer.
Yeah, somebody's initializing something basically, and there's a lot of variations on that theme.
So
And
it's
it
not.
usually goes from nil to not nil one time and never moves again.
Yeah, well, they could. Yeah, but it's not. It's never without a cas. It's either synchronized or cas, but it.
Rarely I can get away without a cas, with only if we're all writing the same value. So
Oh.
if the bit is flipping to 0 to 1 and somebody
Oh.
has to set it that many people can,
Yeah, it doesn't matter who does it.
it doesn't matter who does it. Yes.
Yeah, if I have to scale an image down to a fingerprint,
If I'm doing a
I
right
generate the
barrier,
new object, I flip the pointer from null to pointing at the
Yeah. if I'm
small
doing
thumbnail.
a card mark, a right barrier collector, a standard generational collector using card marks with a right barrier, the right barrier sets a bit in a bit array and a byte array, or sets a byte in a byte array. But it doesn't matter who sets the byte, and multiple racing threads touching memory in the same space will set the same byte. We'll all set it from 0 to 1. We don't care who does it when. So no locking, no cas, just write the damn byte.
I see. Okay.
And you get your synchronization because at a GC cycle, all right barriers were stopped, not in the middle. You're not in the middle of a right barrier update on a GC cycle boundary. And then the GC as a separate thread can read the table of card marks and knows what parts of the heap to scan. So there's yet another one.
That makes sense.
Hog Wild, the deep learning neural network deep learning algorithm does fairly strongly normalizing but arbitrarily random updates to the weights and you get some interesting amount of speed by not casing. You just multiple threads all write into the same weights table, and then they recompute the new learning on the next row as they learn, and they rewrite the weights. And the writes conflict, and you drop writes, and it doesn't matter because it's all fucking asynchronously wild anyhow. And so because it's strongly normalizing, if your model can be normal, if you can get a model out at all, it's almost surely the case that the weights are strongly normalizing. The fact that this one got ahead a little more, behind a little more because you dropped an update or you stomped an update or whatever, yeah, it doesn't really matter. You're all going to end up near the same spot at the same time anyhow.
I saw something that switched near the end. It did like 10,000 generations without locks and then did 12 generations with locks to clean things up.
Yeah, it could be. I mean, I'm trying to remember what HotSpot did here. We went hog wild. We went across a cluster. There was one model per node being beaten on by 16 to 64 threads, cores. And then they as fast as they could, they shared models to prevent the models from drifting apart. But when you got down to the end and you want to declare victory, there might be a zone where you wanted to not have competing folks. I'm trying to remember if we played that game. I know what's going on. Well, I don't know what's going on. I believe what was going on is I didn't want to have competing updates leave the model a little bit worse off than you would get if you had a clean update. Because if two guys said, I'm writing 3 weights this way and you're writing 3 weights the other way, and they conflicted and we got half the writes from each other in a mess, then your overall was worse than one or the other, and there was no correction that followed.
Yeah, but you only really need the last generation to be.
So you wanted one more go round to clean up the last little bits there, and then you walked away. And I don't remember if we did that step or not. I remember we did all kinds of stuff. We had more important things to do, like hysteresis and histogram effects, where the weights would be skyrocketing, or two guys are competing, and one wants to drive the weight down, and one wants to drive it up, and you had to go back and forth with a bunch of things there to make the model converge faster. Once you did all that shit, it worked just as well hog wild or one at a time with locking or casing. You converged faster for all these things, but it definitely converged much faster with hog wild and all the converging special things you did.
Could you write that code in Rust, or would you have to use the unsafe library? I suppose.
Nothing to do with Rust. No.
I was just thinking, if you had strong borrow checkers and who's owning which things, saying
okay.
I want to write the racy for all.
Yeah, so you hand out a bigger shared array. Everyone writes into the array at the array offset of the weight in question. It's an array. There's no locking on the subparts of the array. It's just a big array of doubles, and we're just scribbling on the array of doubles. So the only thing I would do in Rust is say, and 27 threads are all going to have a pointer to the same array. How do you do that in Rust? If I want to have a shared hash table, there's a shared array for the hash table semantics under the hood. They all have to have a pointer to the same shared hash table. They have a pointer to the same shared array. So how do you do that in Rust or in Pony or any of these other languages? There's some way to say it's shared
pointers.
I'm sorry?
You use indices instead of pointers. I feel like that's the thing everybody reaches for first.
Yeah. We're talking about an array. So an array index operation is fraction of a clock cycle on an x86, right? So if I'm striding through an array, L1 access striding patterns, the JIT knows how to strength reduce that to a pointer that does incrementing. It's not actually terribly helpful these days, a little bit. But in the case of the deep learning, which indices, which weights get updated varies every time you go through. You're not updating everybody every time. You're updating a random set. So you don't have a stride one access, so you have to start from the index anyhow, and there you go. So it's all indexes, all random numbers. And hash table, of course, it's random numbers on the indices as well. You hash the index, you modded the table size, or you power of 2 and do an and mask because a mod's 20 clocks still. And you probe in the table, but then you cas. That one's a cas.
Rust has something called slices, which gives you a part of an array.
Yeah, Fortran too.
You can own those separately. I don't remember.
Yeah, okay, that makes sense. Fortran is common with that. It wanted to let different cores beat on different parts, maybe on different systems that were distributed memory because you're a supercomputer and they didn't have memory access. So you wanted to slice it up, or you wanted to pass slices down for just management control.
Yeah, the thing I tend to worry about at slices is I've got a slice that's pointing at 2 bytes in this giant array, but the whole array now can't be GC because the slice is pointing at it as the underlying storage. And
yeah, well, yeah. Yeah, Java arrays have their flaws. One of them is you can't have 2-dimensional arrays that are uniformly laid out without total cooperation from the JIT and the GC. So instead, they're just an indirection pointer. And if you want to stride the wrong way, life sucks.
Does that change with the new value types?
No, it's not related. Not really. You can embed an entire array as a value inside of another array. Maybe you can get multi-dimensional arrays, and maybe they can. I don't know. I didn't look at that level of depth.
That was my thought. If I have my point, which is an X and a Y, and I make that a value, and then I have an array of 4 of them, and I make that a value, and then I have an array of these arrays of 4 of them.
Yeah, and you keep, and you stack it up. So
like make my point and then make my quaternion and then make my array of quaternions.
Right. The goal is you want to mimic a C or Fortran 2-dimensional array where you have C or Fortran style 2-dimensional array striding patterns for the performance reasons. Yeah. In the land of Java, you can get a very similar effect with this cooperative thing with the GC, where the GC guarantees you that all the subarrays are aligned in order, adjacent to one another, one after another in memory, the way you normally get them if you just allocate them in order the obvious way. And he promises that they'll never move apart. So given the base of the mother array, you can get to any of the subarrays by adding the overhead of the padding for the length and the object header, plus the index scaled offset gain. And now you can mimic being a 2-dimensional array like C or a flat 2D array like C or Fortran, and have your loop stride cleverly through them that way. But the GC has to promise that the big old wad doesn't move. And there's another piece to this, which is if the big old wad is big, most GCs will declare you a large object and not move you anyhow. So the moving thing is to compact your heap, but there's nothing to be gained if you're a giant ass guy, because you're going to compact, the size of an average object on a 10 gig array, and no point. So all them big arrays go into large object space, which never moves and never compacts. And you reclaim storage on the page boundary. You reclaim storage by, you actually do compact, but it's the fixed size chunk model of allocation, where all equally large chunks are uniformly, no, that's not quite right, uniformly good. No, he does have to keep them as big separable chunks and shrink combine all the adjacent neighbors and shit. There's a game played, I know, with HotSpot at one of the GCs other, where large object spaces never compact. That was the big one, never moved. But then if you freed them, they reclaimed all adjacent things and aligned them up somehow. I'm trying to remember if that was done at the OS level by virtual, or if they just look for neighbors in virtual space.
So you end up having to think a lot about how you want the memory laid out as you're choosing the layout of your objects. If I want a struct of arrays or array of structs, that looks very different in Java. One of the things SQL did really well is I can have my table create statement that's got the shape of my data and I write all my queries against. And then I can separately come back later and say, oh, I need this index. Add this one index. Is that faster? Delete this index. Is that faster? I don't know any good way to, in a programming language, run those similar experiments of let me reshape this a few ways and see which one of them works best, independent of my declaration of the shape of my data.
That's what HotSpot's for.
Jonathan Blow's Jai hypothetically has this. It's vaporware right now, but he did some YouTube thing several years back where he was like, well, you can put this annotation, SOA or AOS. And
he removed them.
He removed
this feature. Yeah.
Come on.
Shortly after.
Yeah.
Why?
Because reasons. I don't know. It was making the progress of the language harder or something.
Yeah.
Yeah, maybe the Jonathan Blow answer is right, is that what you want to do there is have your struct data shape that makes sense to you, and then have some preprocessor that writes the specific code for how you want to stride it and access it.
I would claim that you want to think about it as a 2D collection indexed in one direction by whatever an array-like thing indexes, and the other way by columns. And this is a data frame. This is a table in SQL. And now the implementation under the hood does what it does based on your access patterns. And maybe you throw some hints down, says I'm probably going to access it this way or that way. Maybe you should flip orientations periodically. But the semantics are, I have a 2D table. I have a table. And the which way it's laid out in memory and how I access it, that's not specified on purpose, so that I can flip around and choose best orientation for whatever the situation is.
So you would say anytime I have a list of dictionaries, call that thing a table and give the programming language the right to do magic on it if it would like.
Yeah. You aren't allowed to ask for a row or a column slice unless it's through an array slice-like behavior with an indirection layer. And then the indirection layer can hide whether it gathers them this way or gathers them this way or indirects you through the table or however it's done, but you're getting not the object that represents the row, because there may not be an object that represents the row, because I've turned you an array of structs, and then there are struct of arrays, and there is no row, single row-like thing. And so you want to hide that API and then say, and it exists, except that it costs you an indirection that either does defensive copy or it says it peeks through with reads and writes, but you're always taking an indirection layer, whatever. You give some weasel words and say, these patterns of access are fast. Walking down a column is fast. Walking across one row is fast. That's two common cases you got to get right. Bouncing randomly between rows and doing something random to each row is not so fast. I mean, that was the H2O model, basically. 2D array, and walking a column was cheap, and walking one row wasn't too
duplicate
bad.
data to make both iterating the row fast and iterating the column fast?
No, the other piece of that was we're expecting you to bulk touch everybody. So you only want to bulk touch once. So you typically had a for loop that says for I equals 1 to bajillion. I only touch it once, and then we auto distributed it. If you wanted to touch separate rows, the getting at a row was the cost of basically a random array element indirection for each member of the row. So we did structured arrays under the hood. If you wanted to walk a row, you had to go get the array and get that offset in the array for that field. So field access wasn't all adjacent to each other. Each field for one row was at a separate array. So each individual array was queried in the middle for a field, which meant if you stride one, walked through the array row by row, everyone got pulled in by the x86 prefetching. They all stayed hot in your cache. It was all happy land cache hits, plus a little bit of extra
because I may be
batching.
pulling off 5 arrays, but I'm pulling off 5 arrays in parallel.
In parallel,
That's actually not bad.
Yes. Whereas if you randomly touched a row, then you took cache misses for every field, which in a real struct, you would take a cache miss to get the base of the field, and then you would get hash hits for the fields themselves. So it was more expensive if you randomly touched all the fields of a random struct. If you touched a random field of a random struct, same cost for all cache misses down the line. If you touched all the fields of a random struct, you paid a cache miss per field in our model, and the struct model says you got 1 cache miss to get it. And the other version of that is if you touched all the fields, one field of all structs, we were stupendously faster because that was your stride 1 axis down the array.
Which is what most data science wants.
Which is what most data science wants. Yeah, they would touch some subset of fields, all of them, and one after another. So if I wanted this field and this field and this field of this row, I wanted them all at the same time, and then I went to the next row and the next row. Well, that was the same as striding down the columns, just 3 columns long stride, which x86 will just prefetch the hell out of anyhow. It's all good. The JIT knows to insert prefetches if it needed to, whatever. Everyone got prefetch. It was all happy land. And then because the similarities in the data on the columns, you typically could compress the shit out of it, and that cut your memory bandwidth down, which was in fact where all the performance came from. Was you cycled through memory 1/10.
Makes sense. I very rarely need to read an entire user object. I often need to read these 5 fields of a billion users.
Well, that's half the performance. And so the other half I'm saying is, if I look down the columns and I'm looking at a column of zip codes, they all fit tidily in 16 bits. So they were column compressed, not as an int. The 4x compression ratio of 16 bits to a full guy meant that I ate 1/4 of the data, which meant that it streamed through your memory bandwidth at 1/4 cost. You could live in your cache 4 times as long, shit like that was going on. So you said, oh, but I also had cities. Well, okay, the cities all turned into an enums. The enums were histogram and compacted and compressed anyhow. So, as you walk through the San Franciscoites area, the compression table said, well, I got 1 million San Franciscoites in a row. This column's all got a 7 in it, only a 7 for this next 100,000 rows. So a little bit overhead, a little bit metadata, the number 7, and a count 100,000 rows. And that was the size of the thing. And then you iterated by just pounding on the same, thing, and didn't actually eat memory at all, or memory bandwidth or nothing. It just went straight through. So memory compression.
That's vaguely what the Parquet file format does. It's going to give you at the top of the file, okay, here is my enum and the 17 strings this field can be, and now it's just got numbers.
We did that, right. We did that per chunk, where a chunk was 1,000 to 1,000,000 elements, all kept aligned, so the rows would be in the same chunk range. But then
my enum of cities only needs the cities that are in that chunk, not all cities.
And we would look at that chunk, and
which is way more likely to be 1 or 2 bytes than all the cities.
Every chunk was independently compressed. Yep, we had roughly 20 compression strategies, and like I said, we would get really good compression out of that. And decompression was plus 2 clock cycles per element to go decompress, way cheaper than the memory bandwidth overheads when you ran out of memory bandwidth.
This was both a disk format and a communication format, or just one of them?
It was not the disk format, but we argued back and forth that we should have done it. It could be a disk format. It was definitely a communication format. It was definitely kept that way compressed in memory. It was never decompressed except in registers. When you handed data between nodes, it went that way. you told that node over there, hey, you want this chunk, and then he took the chunk as a wad of compressed bytes and ate the chunk. And then
I think you pay something for using the same format for transport and disk, because now the schema has to be in the file with the data.
Yeah, if you push
Has
it
to be
down,
self-describing, yeah.
yeah. And that,
But I'm not sure that that's necessarily that expensive as to justify having two separate formats, one that's got the self-describing and one where you have to send a description over, and then you can send a bunch of things that look like that.
okay. So
The main benefit from using the same format is you can pull it, you don't have to keep it in memory.
yeah, you pull it up later. I claim Cameron's right. If it hits disk, it needs to be self-describing, but self-describing can be like gzip self-describing. There's a paper somewhere that describes the algorithm you're using. And the algorithm starts with, there's so many rows and there's so many columns. And then this particular column, it's broken up by so many chunks of this boundary. And then within each chunk, there's a compression byte that says 1 of 20 strategies. Some strategies require more bytes to describe them, like the string to int mapping. In this chunk, San Francisco is the 0 byte, and San Jose is the 1 byte, and Santa Clara is the 2 byte, and the 2 value, whatever, right? And you get your compression. Okay.
And you always lengthen code, and you always stamp it with a version of the spec, because otherwise you're screwed.
Right. You do, yes. That's the disk thing. The in-memory format starts out by saying, we all understand the protocol because we're all using the same jar file to go decompress. Then I have to send over still the kind of the byte and the extra bits per byte, but nothing more. And which protocols are understood can vary from run to run to run, because we'll come up with whatever protocols. I could add a protocol. In fact, that happened, once we got this all wired down and nailed, we had protocols all the time. You went through and you discovered that something was horrifically badly not compressed, and life would get a lot better if you understood the following funny extra protocol. So you
I imagine that sort of logarithmically decreases. When you first start, you find a bunch of new compression strategies you want.
Right,
And after you've been doing this for 3 or 4 years, you're highly unlikely to add a new compression strategy.
That's right. Like the usual one was, we just looked for things that were base plus offset within a narrow range. We just put a base, we had an offset. Then we did a scale. Then we wanted to have integer striding factors that said row number times whatever that was perfectly integer mapped. Then we did a different one for time, for milliseconds, because there's more things you can do with milliseconds that are common. We did the string one after a while, where each column took its subset string, but a node as a whole for all chunks on that node would share the string dictionary.
Are milliseconds really more special than just sort of a double delta encode?
A 64-bit long?
Yeah,
only in that.
My instinct there would be whatever the first timestamp is, you subtract that from everything, and then you want to have a rough delta of about how much does it increase with each timestamp.
Yeah, and so you typically can chop off the high 2 or 3 bytes, because they're all the same with your base offset, and you end up with something that will sometimes fit in 4 bytes and sometimes not. And then, because of the way timestamps work with people, they only monotonically increase, only typically by small variable amounts, but sometimes bigger jumps. So if you break it up into bigger ranges and smaller ranges, and you do an offset, which is I stride you by this for every road, and then I delta after that stride, I can sometimes now squeeze it from 4 bytes down to 2, and that's an interesting savings. So the extra strategy that just works on longs in general, but it's only applicable here, is that I start from the base. For every row, I scale by the row number by X. That doesn't give me the exact number I want. I add an offset. That offset's pretty small now. So I look at this chunk. I say, this guy's sampling once a millisecond or once every 10 millis or whatever his sampling rate is. If I do my stride by that time, his plus or minus deltas are, 1 byte worth kind of things, right? And suddenly the compression, drops again, 2 bytes.
Okay, so I can make that 1 or 2 bytes and maybe reserve one of the numbers that are in that 1 or 2 bytes to say, things are gone wonky. I need to expand back out and start over again. And here's a big
well,
number.
you wouldn't use a strategy if it needed. You looked at the strategy and said it worked for every row, or it works mostly, but sometimes it fails, and that's 2 different strategies. So there's a strategy that says, I never see not a number or not a thing. And then sometimes I have missing data and I have to handle not a thing.
So I have to reserve one of my numbers to be null.
I have a Boolean array and it's all trues and falses and a rare not a missing data. In a chunk where I don't have a missing data, I can go to a strategy that says it's all zeros and ones, it's a bit vector. And then maybe even going further and say the number of ones is very rare, it's a run length encoded thing. Sure. Totally. I mean, these are all and all implemented and useful in the different contexts. But if I have
doing that much math in the registers is still faster than paying the memory bandwidth.
Yes, yes, totally. That's the trick. You get an infinite amount of, not infinite, a cache miss is 1,000 clock cycles to main memory. The data sets always exceed your caches, right? 100% exceed your caches. There's only ever cache missing. So
that's true.
In that
even if I have to add the base and do a multiply and add an offset to that, yes, I'm still talking 4 or 5 clocks.
Even conditionals are much less expensive than going to main memory.
And I still had to do it 8 times for the cache line that came in because I got 8 caches worth of 8 rows worth of data. It was still cheaper by a huge amount. That's the trick. And you said, oh, I had to multiply and an add and an if and a times 4 instructions per clock cycle on an x86.
Unless you are on 6502.
Exactly. You know, if you're on an ancient machine, the trade-off's different. On a modern x86, you can count on having 2,000 to 3,000 cycles worth of instructions per cache miss. And that's a lot of decompression.
Yeah, 2,000 cycles is a fair amount of work.
Yeah. And that just raw performance comes out of that.
I'd
Even
say
on a mix, 2,000 cycles.
300 to 500, I think, is more reasonable. But yeah.
The clock, okay, yeah, the miss, you're right. It's probably 300 clocks miss times 4 per, maybe 1,000 clocks worth of stuff, something on that order. Yeah. Anyhow.
Right, but 300 clocks could actually be 1,000.
Well, 300, you'd get at least 300 instructions. You know, if you're not doing divides.
I think you can get more if you're not doing, if you don't stall your pipe or break your pipeline anyway, you get more than 300 instructions in there.
Yeah. If they're pipeline, they're at least 3x more.
Yeah, that's what I'm saying. It's closer to 1,000.
Yeah.
If you have mispredicted branches and shit, like the algorithm that takes the decompressed data and does something, if it internally makes testing that's not good, whatever, you'll stall up there. But we routinely saw big speed ups every time you threw the compression strategy in. Big speed ups being integer factor. And I'm not talking 10% numbers here. We're talking 2x numbers.
Yeah, it's also queuing theory again, because you've got way more aggregate bandwidth demand on cores than you have aggregate bandwidth available.
Yes, actually that's a very good point. The 50, let's see, as of a few years ago, an x86 would give you 50 gigs of memory bytes per second to and from main memory. But to and from your caches was like in the terabytes a second range. It was much, much higher. So your throttling limit was 50 gigs divided by your 32 cores, your 16 cores. They all got 3 gigs a second of memory bandwidth they could consume.
So ironically, a lot of load profiles look better if you run less physical threads than you have cores, just because otherwise they're contending on main memory.
On memory bandwidth, yeah.
So you're better off adding machines and turning off cores, basically.
Yep. We sold to clients where we had that discussion about what algorithm we're using and whether they should have more cores or more memory, because the balance waffled back and forth depending on what your algorithm was and your size of your memory and things like that. You wanted more cores.
Is that usually a trade-off? I feel like most of the hardware I've seen, core count and max of memory you can stick in the box are highly related to each other.
That's because they add a whole set of memory channels for each new socket. So you go to the sweet spot pizza box, it's 2 sockets. It's got so much memory bandwidth. I can go to a 4-socket version. It'll add some more bandwidth, but not necessarily double.
And you also pay a pretty significant penalty as soon as you go from 1 to 2p, and then also for most Intels, there's a penalty from 2 to 4p. AMD doesn't have the same penalty because they have the crossbar architecture or something.
And when you go to 8, it gets bad.
Right, but the But the main thing is, if you're going to do more than one processor socket, then you actually want to run each workload on each socket only using its memory bus. So you don't want the memory bus spread across two sockets.
Yes, I probably want one process per socket, not one thread per socket.
And the JVM doesn't have any way to dictate, move this memory or this thread.
So your ideal throughput is one process per machine and not more than one socket.
But you would run one JVM per socket.
We ran the one JVM per node because the shared memory effects. Otherwise, when we talk, we can't share memory if you're in different processes.
So what I'd say is that Java doesn't have a strong optimization for socket locality.
Yeah.
So generally, the only way to achieve that is in C++, and it's ugly as crap, and it's very, very tied to the exact version of hardware you're using. So because basically you have to pin your threads onto specific cores. And make sure that the memory that those threads are using are only coming from that socket's DDR buses.
Pin memory, pin threads doing work. Yeah.
There is some hardware specific or actually CPU microarchitecture specific solutions like Intel memory bandwidth allocation, when you can partition memory bandwidth. And that actually gives you pretty good isolation if you care about one process interfering with the other. As far as memory contention is concerned, you can actually solve that to a large extent, but it's very, very microarchitecture specific. So not just Intel, but a specific model of Intel Xeon, for example.
This has been the state of affairs in the supercomputing world for the last 40 years. If you want to get that supercomputer,
Linux would solve that problem by pulling it into the kernel and giving you APIs for these things.
It doesn't, even if they did, it's still a hard problem. It's a hard problem to break up, who's talking to what about whom.
You still need the entire memory subsystem to support that. So from the CPU, through the load and store queue, store buffer, and the cache, you need to partition the outstanding cache miss registers or the MSHRs, because if one process uses up all of the MSHRs by issuing a lot of outstanding cache misses, then all of the other processes are going to be stalled.
Yeah. I'm just saying, we went with statistical probabilities that you would typically, reduce memory bandwidth as in general, because you're always out. Then occasionally you had a process that could use more cores than it could use memory bandwidth, but that's the level of detail we went to. Deep learning could always use more cores, whereas generalized linear modeling always needed more memory bandwidth. And it was stupendously fast and did a decent job. But memory bandwidth bound almost always. Actually, that's not fair. If you had a wide enough columns, it was p squared n, where p squared is the count of columns.
But it was memory bandwidth for you more often than network bandwidth that bottlenecked you.
Oh, yeah. Yeah, that's because we distributed the data and we didn't let you talk cross nodes to get at data as remote unless you really wanted to. So we did a bunch of hacks to make it common that you didn't need to. So all the stride one access guys.
Because you basically have two phases. You have a load the data into the cluster, and then you start processing, at which point you've already done most of your network bandwidth.
Okay, so you're loading a terabyte data set. You don't want to load it through one node, because the one node can only eat it, and he's just going to turn around and hand it back out. So every node wants to eat data independently and in parallel. So the data needs to be distributed already, or you're already screwed on the load times. So however it's distributed, the data spread across disks in your cluster. You hit the load button, they all run to their local disk because they have we distribute the data according to a pseudo random hash based on whatever fucking thing. There's a couple special rules in there, but it guaranteed that statistically speaking, on average, your data was local to you on your disk. And then it was local to you in your memory when we did a computation. The borders of your data would commonly get shared with your neighbor for everyone doing stride one access where they were busy asking a nearest neighbor question, plus or minus a row or two, right? There's a lot of stencil-like calculation things running around where you talk to your neighbor guy. So that meant chunks were in a fixed range of rows, except that the end rows would commonly get shared with the other guy, the other half, the lower set of chunks, the next greater set of chunks. So you didn't share too much. You tried to cut the sharing down to like 10%. Okay, fine. Now everyone had memory local access to their chunks that they were working on. And they didn't want to talk to a random other chunk. And that was a big part of the algorithm design, is that you tried desperately not to talk to random other guys. So in the case of generalized linear modeling, it's high school algebra line fitting, except done in dimensions and more clever functions for different things. Okay, fine. But it's a big scan. And then you need to do a matrix multiply at the end, and that's a p squared, and then a matrix divide with p cubed. So if the row count, if the column count exceeded between 1,000 and 10,000, that was the p cubed one, and that was your bottleneck. And if it was under that, it was n times p squared, where n was a piece of data which we drove down to, like I said, sub clock cycle numbers after everyone did all the right parallel, yada, yada, and memory bandwidth games. You go to deep learning, and it was all about how many computes you can do per second, and memory bandwidth wasn't really the problem. You go to like gradient
Because the
boosted
deep learning is just iterating like crazy.
Yeah, and floating point math like crazy. You go to like a gradient boosted machine, you build a histogram, it's wave after wave after the data, but out of it comes ever larger hash tables. And you have to swap the hash tables around the cluster at each other. And or not hash tables, histograms. And the histograms get big and get bigger and bigger and bigger until you declare defeat or victory and stop. And so you spend a lot of memory bandwidth passing around large histograms. So the numbers, it varied, but nowhere in there did we take a random sample from here to there. You want to do random forest, which talks about random sampling of data. You carefully arranged that you did not random sample trees from other nodes, but you still had the effects that you got that had you sampled from other nodes. So that typically meant you sampled on your node and you built a histogram.
Close to statistically equivalent to
No, it turns out to be horrifically wrong. We tried the one where you every node built a random forest based on its own data and you ran the trees together. Terrible answer. Looks like it good. I'm a comp sci guy. Hey, this is just like you. It's pretty close, right? Long tail distributions, you drop all the long tail distributions. Everybody who's a pattern that only shows if you look at a sufficiently large amount of data never gets showed because you only looks at one node. You got 100 nodes in your cluster.
I got an average case result, but the outlier that I threw out was all the good answers.
Yeah, right. Yeah. Right, all the outliers got thrown out and you couldn't ever find them. So all your long tail distribution answers disappeared. Fine. So the fix was that you built a histogram of your slice, you ran all the histograms together in the log tree rollup. And so a lot of your computation complexity was, I built a histogram, I had to serialize it and send it over the wire to my neighbor. And the histogram was built, shared memory on my local machine, but then I shared it to my neighbor who ate it and folded in with his histogram as a simple walk the array, perfectly predictable, yada, yada, and just sum the arrays together. And then he rolled it uphill to his neighbor. So the array gets compressed, it gets serialized, it gets deserialized, decompressed, done your math, compressed, serialized, passed on to the next guy, up to you get to the root who gets all the histograms, makes a decision on how to split the tree, and then passes the decision back out and we go again. So that's the one where, again, you try desperately to not talk about rows that were not on your local machine, but you went back and forth up and down to dodge it. We did terabyte sorts. There you did a radix sort, which was a big shuffle. But you did a radix sort for a while until every node had a range of data that was going to be on that node. And then you did a quick sort within that node. So it was a lot of steps done that you don't do random access unless you must, and then it's a network hop per element, and that sucks. You can't hold all the data.
I assume sometimes you had to do that Terra sort because you were building indexes over the data that you needed to run the next algorithm.
Whatever people were doing needed a sort step involved. A lot of the fintech data turned into Terra sorts at times.
Because when I think about building a database, like most of what the database is doing is sorting.
Yeah. There's a lot of work put in those. Yes. And a lot of thinking goes into how to handle that. Going back to the olden days, you got tape sort. Fucking go optimize a tape sort. Well, that's kind of what happens now, except instead of tape, it's the network disk top to the neighbor, in and out of a wire. Fine. All right, I've ranted on this stuff
Thank you.
enough. People are yawning their heads off. We should declare victory and walk away.
I think it's helpful.
Oh,
I
and
spent a lot of time thinking about distributed systems and how do you build a nice distributed database and reading all the CockroachDB papers. And
it's a lot of work. Kind of mostly been there. It's a lot of
Pays
work.
well.
Yeah. I didn't do the pay. Well, I guess mine paid me well in the end. Yeah, okay. I walked away okay. All right. I don't think I did as well as you did, sir. I suspect Tangasol coherence did you pretty well. But I did okay.
Larry bought another boat. What can I say?
Excellent. Good to know that somebody wins in the end, even if it's just Larry again.
yeah, we got to work on our being polite with some giving grief on this particular.
You know, if he comes and gives me shit, I'd be goal, bucket list done, right? I am way too small for him to give me shit. He's been given shit by a lot bigger folks than I have. All good. All right, until we meet again, my current theory is I'm still going to try, let's see, when is Christmas? I should actually look before I claim. You guys want to try this the next Friday or not? Is there any yes or no's? I will.
I think I'm going to be working, so why not?
All right, I will throw out the invite. And
next Friday is the 24th?
4th, yes. I know I have families showing up where you have special dinners being made, but this will be in the morning, and then it's okay then. All right, it's fine. So I'll throw out the invite.
It's 5 o'clock somewhere.
It's got. I'm sorry, I missed.
It's 5 o'clock somewhere.
Yes, that's true. All you people on Christmas Eve days, whatever, can just vote with your feet. All right, till we meet again.
Thank you.
Bye.
Yeah.